Hello, welcome to the last video of this series, which was a bit different than the other videos, because in this video I will present you with simulation results where I introduce the mistake by purpose and I ask you to find the mistake. But let's walk through this in detail. So whenever you see a simulation result, it can be the simulation you made yourself or the model simulation results by someone else that are presented to you because they want to prove something with the simulations, because you are supposed to continue their work or use the results for then some kind of other analysis. In any case, it is always important to critically evaluate the simulation results. Right? And this really is an important step whenever working with models. And again, independent if it's your own model, if it's a model by someone else. Because only when you critically evaluate it, you avoid to get into pitfalls and have a wrong analysis simply because there has been a mistake in the simulation. In the last video, I talked about the quality of simulation, and we discussed a bit how you can see that in terms of these parameters or these properties, better to say, the properties of a numerical simulation, boundedness, consistency, and so on. It has been the quality check. We also discussed in the same video, so the last video, an applicability check, which is kind of difficult. I cannot really train you on it, but it goes on the conceptual level, right? So you have to ask yourself, okay, this are the physics, the ongoing processes, are they captured accurately, all that kind of thing. This video here is more about low level mistakes that have been done, because making mistakes is that's human, and modelers are not any kind of other, so we make mistakes all the time, and things like this, for example, go to having a wrong parameter, having forgetting the wrong sign, not choosing boundary conditions correctly, or having the wrong choice of geometry influencing the simulation result. Again, I will show you examples of this in this video. So if it sounds a bit abstract right now, it will become more clear with the next couple of slides. But it's about making mistakes and how to identify them. And this is just giving and trying to give you tools by the hand that you can use to check if you did everything right. Because as again I said, you usually would do some verifications and validation, having analytical solutions and so on by the hand. This is not always possible, and maybe even you have done that, but still, stupid mistakes can happen. And do not get fooled. So often see people who start modeling and they run into a problem, they find a mistake, and they question their model on a very, very basic level, conceptual level, which in principle is okay, but to be honest, most errors are trivial. This is sad. Forget a minus sign somewhere, took the wrong units, stuff like that. Trivial things which can be damn hard to identify. It's not like that the error is trivial, that finding it is also trivial. Okay, but it and this is what this video is about. It is about helping you how you can identify trivial mistakes in the simulation. So this lecture incorporates 6 different scenarios, and it will always be based on 3 slides each scenario. So we'll start with the scenario description. Then I will show you simulation results where they are erroneous, so they have a mistake in it. And then I pretty much ask you to, or recommend you to pause this video, look at the results in detail, and then, try to find the error, and then continue, go to the next slide, where I will tell you what kind of error occurred and how you can detect it. Okay. Of course, if you don't find the mistake, that's also fine. This video is for training you, so go to the next slide then, always to find what has gone wrong. Right, but I really recommend you to take time and look at the results. Sometimes a bit more figures, sometimes there's just one or two, so there isn't too much to see, but it will highlight you, the results. Let's start with the first scenario. This is like the basic scenario. So when we go now to scenario 2 or 3, it will often be just variations of this kind of scenario. So let's take a look at it. It's completely simple. We have a steady state groundwater flow, okay, in a slightly heterogeneous aquifer, okay, mean hydraulic conductivity, okay, values given, 20% variation of that value, and a porosity of 25%. Okay, so hydraulic gradient, 1% from west to east, so we have a flow left to right. It's unconfined aquifer, that's also important. So we have a water level height of around 39 meters, okay, and then we have 1% decline from left to right probably. So this is around 6 meter depth to the water level from the surface, which means we have a top surface of 45 meters, and the modeling domain is 100 times 100 meters. Well, that sounds fair so far. Let's take a look at the results. So we have an hydraulic gradient from 38 to 39 meters, from 39 to 38 meters, 100 meters, 1% is 1 meter. Well, okay. We have a velocity, well, we see the heterogeneity in X and Y direction. In X direction, again, it's higher than in Y, which makes sense because we have the hydraulic gradient and we have a heterogeneity. So this is where we have a significant contribution in Y direction, but of course it is less than in X direction just because of the orientation of the hydraulic gradient. So, can you spot the mistake? The test here was that the flow velocity is surprisingly high. Right, for this rather low hydraulic conductivity, 10 to the minus 4 meters per second, we would expect with this hydraulic gradient a flow velocity of maybe 10 to the minus 6 meters per second. But if you look at the slide, it's magnitude larger. And this is because I made a mistake by purpose, forgetting one of the O's here. So I just had a hydraulic conductivity of 0.001. Right. As we have shown the image of the hydraulic gradient, which was correct, well, it is very easy to derive that the hydraulic conductivity might be wrong. Right. So this is difficult maybe to see if you do not have experience for the numbers, but this is one important lesson to learn how to critically evaluate numerical simulations. Do quick analytical checks. Calculate flow velocities. What would you expect? It is heterogeneous. You can't, get the right exact value, but is the order of magnitude correct? Right? So this is the first check, which you always can do. You can do this for the hydraulic gradient. Right? If it's given in percentage or if it's given in meters, do the conversion, check that it is correct for that the boundary conditions are set correct for the spatial domain you're looking at, right? Things like this. flow velocities calculation, also transport velocities, right? Consider tracer transport going from left to right. Check, okay, where's the peak? So at day 1 it's here, at day 100 it's over there. This is maybe 250 meters. What kind of transport velocity matches that, and is this what we would expect? Right? Things like this, quick estimations, quantitative estimations using calculator and pen and paper, just to make sure to avoid such kind of mistakes. Okay, lesson learned. Let's go to the next scenario. So it is I will take scenario 1 as the base scenario with the wrong velocity. And now we simulate a tracer test. Okay, we are injecting 50 kilograms of material 5 meters from the east boundary. 5 meters to the east from the western boundary. That makes kind of sense. From north to south, it's in the middle of the domain. And we have a given diffusivity value, we have a given length, dispersive length value, and there is no retardation. Well, okay, sounds straightforward. Let's take a look at the results. So, okay, we see here our injection point. So it's after 1 day. So this 5 kilograms have already diffused a bit. Okay, we see the diffusion is continuing over the days. So here with the concentration at day 10, and here's the concentration at day 20. Well, you might have already spotted the error, so I won't keep talking and just see you again on the next slide when I present you the solution. Yeah, you might have already spotted it. It is repetition from last video. The solution is, well, unstable. Again, it is implicitly stable, but it shows indications of instability and inaccuracy. Because, for example, we're violating boundedness, we get pattern that are unphysical, they're not explainable by the heterogeneity we have here. So it's again this kind of wave shape here, I think very clearly visible, also hopefully for you on your screens. So yeah, that was quick and dirty repetition from last week to show you again the instability here. Quite a simple one. So having the next scenario, which is also again based on scenario 1 with the wrong hydraulic conductivity, we are conducting now a pumping test with a pumping rate of 1.5 cubic meters per second in the middle of the domain. Okay, fair enough. That doesn't look too complicated. Let's take a look. Oh, we do not get a result. We get an error message. Simulation does not converge. Why? And what can you do to constrain your mistake? So this is, this is one of the classical situations now. You're trying something and you get an error. What can you modify? So you already know, well, okay, without the pumping, it worked. Now I'm adding a pump and it does not work. So what can I modify to see if it works or not, or to constrain the mistake? Think about it. I'll present you the solution in the next slide. The point here was that the given pumping rate of 1.5 cubic meters per second, I mean, you have to think about it, 1.5 cubic meters per second, that is massive. This is just massive, okay? You convert it to liters to see how much water per second you're supposed to pump here, okay? This is crazy. So what you probably pretty much do is, with 1.5 cubic meters per second, you would just empty your aquifer, okay? So I reduced, my technique here was to reduce the pumping rate to a level which I know was reasonable, like 0.1 cubic meters per second, which is still a lot, but something like this, and then moving upwards to see when I reach this critical level. And you see with 1.25 cubic meters per second, we already lower the groundwater level to 3 meters at the position of the pump. Okay, and of course the system fails, so it cannot converge anymore once the value becomes negative. Okay, and this is what would happen if you pump with 1.5 cubic meters per second. All right, so this is why we try to train you as lecturers in applied sciences always to get a feeling for numbers, right? Get a feeling for what kind of rock and soil, what kind of hydraulic connectivity you should associate with this kind of soil or rock. Get a reasonable, what are reasonable pumping values? Okay, so that's like 40 liters per second. If you go to industrial pumps in terms of mining and so on, okay, you will get larger values, but here we're talking about an aquifer system of 39 meters of hydraulic head. All right, so get a feeling for numbers, because it will help you. If you get intuition, it will help you here to check if this makes sense or not. Okay, there's also another mistake in the simulation actually, but I will discuss that in another scenario. First, let's do a different mistake. So, well, as I said, there was some transmission error of the units. Okay, we corrected the pumping rate now by a couple of magnitudes from the scenario straight, and we now get the following results. So same thing, you know, groundwater flow from left to right. This is what we get. So we have here the hydraulic head from left to right. Well, there you can obviously see our pumping station. Well, what could have gone wrong here? Well, it's a mistake of the error of the sign. I fool you here because I only showed you the hydraulic head. If I have shown you the velocities as arrows, if I have shown you the profile line, you would have seen more clearly that the hydraulic head here is increasing or not decreasing, right? So it's the yellow spot here, and you see yellow is associated with the higher hydraulic head and should be lower if we are pumping actually. So we are here injecting instead of pumping. A simple mistake by the sign, right? Pumping rate, of course, is given with a minus in the source term because we are extracting mass. But in those nice 2D figures, and you're thinking, right, now you might have seen, well, that's obvious, but imagine you have a 50, 70 pages of report and you see tons of those kind of images. And in one of those images, such a mistake, then you can easily miss it. And this is why I emphasize this over the whole course, visualization is so important. Because if I have shown you the arrows here, not the arrows, but the arrows of the flow velocity field, right? Even in a contour line, you might have missed it because you would have just have seen, okay, the contour lines go closer here and they get larger, wide. But while still, you might have seen more those kind of bending, which could have made you skeptical. But really, velocity field would have been the most obvious for me, or the profile line. That's why I showed it here to you, right? Then this would have been more clear right from the beginning, and you see, okay, well, that can't be, right? So remember two things: visualization is crucial, and the other one is, these examples might seem simple here, but again, remember, report 10, 20 of those kind of simulations. You might miss one. That's wrong. So now we actually want to inject. Okay, so we use the same base scenario one. All the parameters, they stay the same. But now we want to extract it. So I made a little bit of story here. Imagine you have a borehole for geothermal energy at a deeper aquifer where you get higher temperatures, but for whatever reason, you usually don't do that because you inject back to the aquifer where you extracted it. But let's say here you want to inject the water in the shallow, in the unconfined upper aquifer system of this rather conductive aquifer, which is good because it allows you high pumping rates. Yeah, so let's see what's happening wrong or what's going on. Again, I'm just showing you the hydraulic head distribution, and what we see here, there's a strong increase, so we are injecting a lot. What could be wrong with that? Well, the hydraulic head is above the surface. I know it is a long time before. On scenario 1, I told you that we have a hydraulic head of 39 meters with 1% decline of 100 meters, so we have 39 to 38 meters in our modeling domain. But I said the top surface is at 45 meters. Or, well, I told you that the distance between groundwater and top surface would be 6 meters, so 39 plus 6 would be 45 meters. There is a couple of lessons again I want you to learn from that. First of all, this is exactly what happens in those kind of reports, scientific papers, technical reports, whatever. There, somewhere in this work, there's probably a table with the parameters, probably appendix or something like that. And you just see all the nice results in between. So this mistake was easier to detect for those people who went in scenario 1 and wrote down the numbers on a piece of paper and just checked it here again, or which went back and forth between the slides. So take those values, look at that, right? Hydrogeologic or groundwater modeling is a quantitative science. It is about numbers, so you have to have your numbers there. The second lesson is also about numbers, because the computer is just crunching numbers. The computer barely worries about if it makes sense what comes out of the simulation. Well, again, depending on the developer, it might have some catches in there and say, for example, well, hey, you're resulting in a negative hydraulic head. That can't be. Check your simulation. But this is just whatever the developer, the programmer included into the code. And well, I can tell you from my personal experience as a software developer, it is very difficult to think about all the mistakes a user could do and then write a routine to ask and to catch those kind of errors, right? This is impossible. So what you have to do is, you as a person to check the simulation are the one with the understanding of the system. Okay, so you have to make, does it sense, does it fit my expectation? And know if you inject so much that your water is above the surface, then your physics are not describing the situation adequately anymore, because everything that is above the surface is not porous media anymore, first of all. And secondly, this is of course hydrogeological or groundwater management wise not a situation you want to have. Okay, so this is your job. That's why companies, that's why public service or so on will pay you, because you are the one thinking about if it makes sense or not. Okay, the computer is not doing that for you. The computer is just crunching the numbers, and as long as the system itself, so that the mathematical system converges, it can obtain a solution, the computer will just simply show you the solution. Okay, and it's your job to make sure this numerical result matches the real world. We're coming now to our last scenario, which is a bit different, and it's not. So we switched. So we are in a confined aquifer with just 25 meters of thickness. I kept the hydraulic head of 35 meters and I kept the hydraulic gradient of 1%. The idea is to conduct a pumping test, okay? And we really want to look at that in detail, all right, with a high spatial discretization of 0.1 meters. Okay, however, if we want to keep it with that high resolution, we need to decrease our simulation domain to 10 by 10 meters, pardon. Which is okay. I mean, we want to look at it in detail, so we are zooming in. Okay. Well, because we are in confined aquifer, we have some kind of stratigraphy, we have the hydraulic conductivity, and we have a pumping rate, 0.01 cubic meters per second. Okay, sounds fair enough. Let's take a look at the results. So here again, you're seeing two figures, so I'm not hiding anything from you. We have the 2D hydraulic head. We have 39 meters here. Well, because now remember we're just on a 10 meter scale, so of course the hydraulic gradient would be is way less because it's 1%. So on 10 meters, right? It's just 0.1 meters. So this is why both borders are yellow, and we have our pumping station here in the middle, which goes down to 38.74 meters. Okay, fair enough. And we get here our nice pumping cone, so that all matches. Well, can you spot what has been done wrong with this in this simulation? The mistake here was that the domain is too small. So imagine you have this simulation. If you want to have that hydraulic gradient, you have to specify your boundary conditions by directly boundary conditions left and right. Okay, so we have 39 meters on the left and we have 38.9 on the right. Pardon, 39.99 because we're just in 10 meters. So this is what we have on those two values. Right, so those are fixed. This is our boundary conditions. And now you're pumping. But your pumping cone cannot develop freely because those 2 points are fixed. You see, it's not going into this hydraulic gradient that it would have, right? That would need. This is not there because I fixed those two values and I'm just drawing down here. If you do this pumping test on a much larger domain, well, the 1,000 meters is too large, but I want to show you here, you just have a declining groundwater level to 38.75 meters. But because those values are fixed, as again, this cone will not develop fully. If you give it enough space, it will go down to something like 38.25 meters. So there is half a meter wrong in declining groundwater level predicted by the pumping. So that could be substantial. And now you see here, okay, if I'm on 1,000 meters, of course I have a much larger hydraulic gradient here. So I have the 1 meter over the 1,000 meters, all right, because I switched from 1% to 0.1% in hydraulic head. But you see that the cone is, well, maybe 100 meters. Let's say this one is in the middle, so this is 500 meters. So there's still like 100 meters cone developing. You know, at least until to be really sure that the boundary conditions do not influence my pumping test, right? Because even small variations could matter here. So the fact here was simple. The domain was chosen too small, and the result is too strongly influenced by the boundary conditions. All right. Here on the right, I did the extreme. I know 1,000 meters is an extreme example, but so you can nicely see how things develop and how it should look like. So the lesson I ask you to learn here is, well, first of all, study the influence of boundary conditions on your simulation result, but also to have, if you want to look something in detail and close and with high resolution, start with a wide view and then narrow down. This mistake would never have happened if the person would have conducted and say, well, okay, let's play this safe. Let's start with 1,000 meters and then narrow down on what I can have as maximum numbers. The other point is you could analytically compute what kind of K you need to expect for that kind of pumping rate under this conditions. So this would have been the other alternative to use analytical solutions here to get an estimate. Of course, this would have been also a recommended way. Better would be both ways to be absolutely on the safe side, because then you already would have a verification comparing your simulation results with the analytical solution. So let me conclude. Actually, there is a lot of things to learn from this lecture. First of all, there are a lot of possible error sources when doing numerical simulations. And you have to imagine here there have been all just completely synthetic cases. So, when you're dealing with data, you can load in the wrong borehole locations, or associating the wrong borehole locks with the borehole points, and mixing up laboratory tests, soil types, whatever, so on. So very many things that can go wrong, and something will go wrong. This is human. Mistakes will happen. The best thing you can do is to critically analyze the numerical simulation and try to catch as many mistakes as possible. Catching errors, you might have observed, is sometimes super easy, because from those 6 scenarios, probably a few have been extremely obvious to you. Maybe some have not been obvious to you. And if you ask your peers watching the same video, you might find that, well, actually some will find different scenarios obvious and others will, others don't. So this is also kind of a personal perspective and what you see and what kind of methodology you're applying to analyze. The other important thing I want you to learn is that the computer is not thinking for you. The computer takes care of the math, but it will do what you say. And if you say something wrong, the computer will do wrong. It is your responsibility to think. It sounds obvious, but sometimes people, when simulating, forgetting to think. And this is not good, because the computer won't do that either. So, I mean, the thinking process starts at the conceptual level of the model design. But also, and this is what I want to say here, is also when analyzing numerical results, right? And to critically question any simulation result is crucial. So when someone presents a simulation to you, I hope for those 6 scenarios you learn some techniques, some points to take care of. Comparing values with analytical solutions, with quick calculations, does it make sense? What kind of flow velocity to expect? Things like this. And you are here now on training, but if you do this for a couple of years professionally in a company or so on, you will get a feeling for quantities, and this is what you probably already get tried by your lecturers and professors to go teach, getting experience for quantities and values. This is something that comes with experience when you work in the job, and then you will get a numerical simulation and you will say, well, that kind of flow velocity is not what I expect with that kind of soil type, for example, right? of course, depending on the hydraulic gradient, but you will find that, well, regions will have not so much variation in hydraulic gradient usually, so you can, you know, easily associate that. And the variation in soil type, hydraulic conductivity of soil types is much larger. But that's not the point here. The point here is that, you know, having quantitative analysis is one point, but also, you know, geometry choice, thinking of scenario 6, having also this analytical estimation about, okay, what kind of cone do I expect for the pumping? Stupid things like this, sign errors, stuff like that. This is so crucial, and people can easily fool you with simulations if they want to. Okay, so I hopefully you also learned that depending on the visualization, I can hide things for you. I can make things less obvious. And you know, if you're working for public service and it's your, you know, some company wants to have a pumping installation or so on, and then it's they will conduct simulations, and it's your task to critically estimate these kind of, or assess those kind of simulations. And then do not get fooled by this, asking for the right visualization, asking for the numbers. This is also an important lesson from this lecture. And taking about the same thing pretty much is here, and also coming to an end with this lecture series. This was just about giving you a very, very quick and rough overview about numerical techniques with special emphasis on application in groundwater modeling. You can study for years about numerical techniques and numerical methods. And, well, I recommend doing it because it's fun, but it might not be for you, depending on your personal preferences. But that you attending this lecture series here with a geoscientific, geological background means you want to combine two skill sets. You have your strong hydrogeological, hydrological, geoscientific, whatever it is, background, and now you learn something about modeling. So you want to combine those two skill sets, and this is what people will hire you for. But that doesn't mean that you're now just conducting simulation or looking at the simulations and just, you know, take it as it is. This is where the thinking comes in, because now you can associate, is this a high quality simulation? Is it stable? Is it bounded? Does it converges? All that kind of things you can assess. And on the other hand, you have the geoscientific background to understand if the results make sense in that kind of purpose, right? Is it reasonable for the soil types, for the aquifer system you're looking? This is these unique skill sets you have now, and this is what I ask you to use in the future. Thank you very much.